So in order to talk about quantum mechanics, we have to understand a little bit about light. And so we're going to take a brief jaunt into physics here. The interaction of light with matter has helped us to understand the atom and was important in developing these models of the atom. So we need to understand what light is. Light is a form of electromagnetic radiation. It's a type of energy. Light travels through space at a constant speed. We call it the speed of light. 3 times 10 to the 8th meters per second. As you know, meters per second doesn't mean much to us. That's 186,000 miles in a second. It's really, really fast. Light travels faster than sound, which is why when you see lightning, you hear the thunder a little bit later, and why you can count the time difference between when you see the lightning and when you hear the sound, they were generated at the same point in space and in time, but the sound takes longer to get to you. You can estimate how far away the lightning is by looking at the difference in the time between when they come to you. Fireworks, you see the flash and then you hear the bang. It's closer because you're usually closer to the fireworks, but there's a difference in speed there. Light is a funny thing. It has properties of both waves and of particles. Okay. The wave nature of light is probably easier to understand than the particle nature. We think about waves in water. Here's a picture of a water surface that's being disturbed by water drops falling onto it. And we see that as the drops hit, they disturb the surface of the water and they cause ripples. And the ripples travel outward in a nice circle unless they run into something. One of my fond memories from high school was in physics class, and we had these ripple tanks. There were these shallow tanks of water that were elevated, and then they had a light above them. And you would put a paper underneath, and you could set up standing waves in the water, and then the light would shine through, and you could draw the waves on the paper and actually measure the distances and do all kinds of fun calculations and stuff. Of course, by the end of the time that we were working on them, they did get a little smelly because they weren't chlorinated or anything. But that was just a fun time in high school physics class. But the waves of water behave much like the waves of light do, and they carry energy. Do you remember the tsunami that hit in Indonesia? Do waves carry energy? Waves carry a tremendous amount of energy. You know, there's an earthquake in one place, and those waves carry that energy to another place and cause just unbelievable disaster. So waves carry energy. Here's I guess you could call this a graph of a light wave. It's basically a sine wave. It goes up and down. It's very uniform and regular. And it has characteristics that we can measure. One of those that's important is the wavelength. The wavelength of a wave is the length of the wave. Right? It's the distance between two high points, two crests, or you could measure the distance between two troughs, but that's the length of the wave. For visible light, this wavelength is what determines the color that we perceive it to be. Remember, all light is traveling at the same speed, 3 times 10 to the 8th meters per second. So we have the wave traveling, and it has a wavelength. If we pass a light, such as sunlight or a light from an incandescent light bulb, through a slit and through a prism, we get a rainbow, don't we? We've all seen this happen. In fact, just on the way, my kids, of course, missed the bus this morning and all chaos ensued. And on the way to driving them to school through the traffic, one of Michael was saying to Andrew, "Do you see the rainbow?" Because something in the car was acting as a prism and making little rainbows in the car. And I wasn't even thinking, oh yeah, I'm going to lecture on that this afternoon. Just so I can get out of my way. I've got to get to school. But we've all seen this. It happens after it rains. where the water droplets in the air are acting as tiny prisms and separating the light. White light, such as from an incandescent light bulb or from the sun, white light contains all of the wavelengths of visible light. And so it has all the colors. We call that a spectrum. And so it has this whole range of colors. Color's really kind of a fascinating thing. In this picture, this woman's wearing a red shirt. Why is it red? It's red because that fabric is absorbing all the wavelengths of light except red. And it's reflecting the red, and that's what we see. So when you see the sweatshirt is green, you're seeing the reflected green, pink shirt back there. A lot of people wearing black today. I'm wearing dark colors too. It was an exam day. We're all kind of somber, right? We're in mourning. But black absorbs all light, and white reflects all light. Have you ever been outside in the hot, hot sun here in the valley summer? And if you have dark hair, your hair just gets really hot, doesn't it? I've got light hair, but my husband has black hair. You touch his hair and it's like, oh my goodness, it's so hot. And mine isn't that hot because mine reflects most of the light and his absorbs it. If you have a dark colored sweatshirt on, it's going to be much, much warmer than a white sweatshirt. And sometimes that's a good thing and sometimes it's a bad thing. But the light is reflected, and what we see as color is the light that's reflected from something. All the other wavelengths of light are absorbed. Another characteristic of light waves is frequency. Frequency is the number of cycles or the number of crests that pass through a stationary point in 1 second. And the wavelength and the frequency are inversely related. So let's draw some pictures here and see if we can see how this works. So I'm going to draw a wave. It's going to be ugly because I've had too much or not enough caffeine. No, I'm pretty sure it's too much. So we'll see if we can do this. So there's a wave. Not exactly a smooth sine wave, but you get the idea. And it's moving this direction. And here's a little person. And that person's standing there and counting as the wavelengths go by. So he's counting, and as the wave passes, 1, 2, 3, 4 in 1 second, then it's 4 cycles per second. There's another unit that we use for that. It's called hertz. Nothing to do with Hertz rental car. It's abbreviated HZ. And it's cycles per second. It can be cycles of anything. It could be revolutions of an engine or rotation of a wheel, but it's cycles per second. So there's one wave. Let's do another wave. So here's another wave, and it's traveling at the same speed, going this way. And now when this guy counts it, is he going to see more crests pass or fewer? He's going to see a lot more, right? So let's look at the difference here. This is the wavelength, which is lambda. It's a Greek letter. That's the wavelength of the red one. It has no correlation to the color red. I just picking random colors. And this is the wavelength of the yellow wave. So the yellow wave has a longer wavelength, but its frequency is lower. The red wave has a short wavelength, its frequency is higher. And so the relationship is, we say it's an inverse relationship. Frequency is the Greek letter nu, which is like a V, but not a V. So nu is not equal, is proportional to 1 over the wavelength. If the wavelength is big, the frequency is small. If the wavelength is small, the frequency is large. Yes, question.
Proportional symbol, is that an alpha? Or is that...
That's a proportional sign,
It's like a...
which is like an alpha, yeah. It means proportional to. You could also say that nu equals some constant divided by lambda, if you like that better. The important thing is if one is bigger, the other is smaller. That's an inverse relationship. So that's the wave nature of light. We can also view light as a stream of particles. And this might be a little harder for you to swallow. You've probably heard the word photon, though. If you've ever watched Star Trek, you've heard them say, "Fire the photon torpedoes," right? Well, what is a photon? A photon is a particle of light, a piece of light. It's a packet of light energy, a little packet of energy, a piece. Okay, so photon, a piece of light. Yeah. So just...
I heard somewhere that they were able to attach a photon to an atom or a photon particle to an atom and they created a new type of molecule.
They fired photons through tungsten and they forced them to create molecules.
Interesting. See, that gets into physical chemistry and quantum physics and things, which I find interesting, but I don't keep up with.
You know what is a photon? Is it just a wavelength?
Well, what is a photon? And that's hard to understand. Have you heard of Einstein's theory of relativity? It's kind of tied up into that. As we take an object and it gets smaller and smaller and smaller, it's still an object. Like you think of a baseball and you shrink it down. You shrink it and shrink it and shrink it. And as it gets smaller and smaller, it's still a particle, and yet it can behave like a wave as well. And its wave characteristics become stronger. And actually the idea is that all things have wave nature and particle nature. But when the object is large, like a baseball, we can't really observe its wave nature. So with light, and we'll also see with electrons, which are crazy small as well, they can act as particles and as waves. And it is something that's very hard to get your mind around.
So what forms a proton then?
Well, a proton is almost 2,000 times larger than an electron. But a proton would also have wave characteristics. So all particles have wave characteristics. Yeah, these are things that are just really hard to understand. So just say to yourself, a photon is a piece of light. That doesn't seem possible, but she said a photon is a piece of light.
Is it the smallest piece of light that you can break down light into? Or is it
Well, yeah, pretty much. A photon has a certain energy. And so light with a certain wavelength is going to have photons with particular energies. So you can't have bigger photons and smaller photons, but you can have photons from different wavelengths of light that will carry more or less energy. I know.
That makes sense.
Does it? Good.
Isn't there another one that like, you can't measure the energy of photon and when it arrives?
The electron. You can't know the position of an electron and its velocity or direction at the same time. Which is, yeah. That's enough of that. A photon is a particle of light. It's a piece of light. And that is hard to understand. But you can do all this stuff without thoroughly understanding that. Okay? Sometimes you just can't understand everything. And so you just have to let it go. Okay? Really, you do. The amount of energy carried in that packet is going to depend on the wavelength of the light. The shorter wavelength is going to have greater energy. And So those light waves, if their crests are closer together, if their frequency is higher, then they carry more energy. And if you think about that, well, I've erased it now, but let's go back to those waves. Oh, that's white. I didn't want white. So the red one was like that, kind of, and the yellow one was like this. Which one of those looks more energetic to you?
The red.
The red one. It's like going up and down like crazy, right? They're both moving at the same speed. It's a little bit like Grandma and the 3-year-old walking down the sidewalk. And Grandma's just walking slowly and steadily, and the 3-year-old is doing zigzags and circles around her, right? And he's just moving. They're going at the same speed. They're getting there at the same amount of time, but he went all over the place because he had higher energy. This high frequency, short wavelength light carries more energy. And I'm telling you all these little stories and stuff because you need to remember that short wavelength has high energy. How do you do that? Well, imagine the picture. So short wavelength has higher energy.